We'll start by opening Google and searching for Visual Studio 2022 Community Edition. Just click on the Download Visual Studio link and then execute the setup.exe when prompted. Click Yes to allow the Visual Studio installer to run, and then also click Continue if prompted. Next, we're presented with a variety of different workloads that each contain the components required for any given programming language. The most popular language to use with OpenGL is C++, so go ahead and select Desktop Development with C++ and click Install. It'll take a while to download, so I'll speed up the video for this part. After it's finished downloading, it's recommended to restart your computer, which obviously means you'll need to reopen this video to resume from here. Next, I'm going to add a shortcut to the taskbar and then finally open up Visual Studio, and then it'll ask you to sign in or create an account if you don't already have one. After choosing a colour theme, select Create a New Project and then select Empty Project and click Next. When it comes to renaming the project, I prefer to add Project after the project name and Solution after the solution name, simply because it makes it clear when navigating through the project's folder structure. Next is to download and set up GLFW, which is a library that creates the window that our games or graphics will be displaying in. Two options are to either build GLFW from the source files or instead use the pre-built 64-bit Windows binaries, which is the option that I've gone for simply because it's the easiest. After the download is complete, you can unzip it. Next, at the highest directory level within your solution folder, add two new folders, one for the include files and one for the libraries. Next, open the glfw.bin.win64 folder, within which open the include folder. Within that include folder, copy and paste the GLFW folder into your own includes folder that you just created inside your solution folder. Next, open GLFW's lib-vc 2022 folder and then copy and paste the glfw.lib file into your own libraries folder that you also just created inside your solution folder. We're going to be using GLAD, but there is also a GLAD 2, both which work perfectly fine. Once the GLAD loader generator page has opened, select version 4.2 from the API's GL drop-down list, and then select Core for the profile compatibility. There's no need to select any extensions, and make sure you leave the Generator Loader checkbox as checked, and then click on Generate. Next, download the glad.zip file and then open it. Inside you'll see an include folder. Open that include folder and copy and paste the glad and KHR folders into your own includes folder. Next, return to the directory level in which you located the glad include folder, but this time open the source folder. Copy and paste the glad.c file into your own project folder. Now we need to add a new C++ file, which we can do by moving the mouse pointer over the source files folder, pressing the right mouse button, selecting Add New Item and then selecting C++ file. We also need to add the glad.c file to our project. Press the right mouse button again, but this time select Add Existing Item and then select the glad file from your project folder. We need to tell the IDE where to find the include files and which libraries to link with at compile time. Click on your project name and select Properties from the project menu. Within VC++ directories, click the down arrow to the right of Include Directories and select Edit. Start typing in the location where your project folder is located. Use the up and down arrow keys to select the correct subdirectory and press the / key to select each progressive subdirectory. And then finally select your includes folder and click OK. Repeat this process for the library directories. Next, under Linker, click on Input. Click the down arrow to the right of Additional Dependencies and select Edit. Type in two entries, OpenGL32.lib and GLFW3.lib, and click OK. And then click Apply in the parent window. So now let's look at the toolbar options. Notice that there's no cut, copy and paste by default, so you need to add them manually as I'm doing here if you want them. This next step shows you how to install the GLSL language integration extension for OpenGL shaders, such as vertex shaders and fragment shaders. It provides syntax highlighting, keyword suggestions, and it also allows you to collapse and expand the function bodies. If you don't install this add-on, then your shader code will be displayed as ordinary non-responsive plain text, although it will compile perfectly fine. If we open up the menu options page by clicking on Tools, and then we select Options at the bottom, and then GLSL Language Integration Configuration, we can see the various file extensions supported. The two we'll be using to begin with are .vert for our vertex shader and .frag for our fragment shader. Just to show you a comparison of what it looks like with versus without using the add-on, you can see different variable types being suggested as I'm typing. For example, vectors, vec3 and vec4, and matrices, map3 and map4, and also numerous OpenGL variables such as GL position, GL frag color, and GL frag depth. By clicking on the plus minus box, you can also collapse and expand the function bodies like you might expect. Now, if I disable the effect of the GLSL language integration by deliberately changing the extension to an invalid name, you can then see that it's now just a completely plain text file, although once again it will compile perfectly fine, no different to when using valid extension names. Now let's take a look at the code. You can either type in the code as we continue, or you can copy and paste it from programmingcreatively.com. We start off by adding two include headers, glad.h and glfw3.h, and we also include the input-output stream because we're going to output text to the console window. We then initialize GLFW, which enables us to use all of the library's functions. The GLFW window hints major and minor are optional, but by setting some minimum requirements such as OpenGL version 4.2, it makes sure that the program exits if the PC running the application needs to be updated. OpenGL is also backwards compatible, which means that computers updated to later versions such as 4.3 through to 4.6 are also okay. Different people are naturally going to have different screen sizes to one another, depending on their monitor and personal preference. And so we can use GLFW to discover which screen size is currently in use by calling the GLFW get video mode function and using GLFW get primary monitor as the argument. Once we have the screen size, we can then use it to calculate the window size and also position the window to be centered on the screen by calling GLFW set window position. In this example, we're creating a window that is half the monitor's current display resolution. Next, we load the OpenGL function pointers by calling the glad_load_GL_loader function. We then set up a few variables and proceed to create the main while loop, which is commonly referred to as the main loop. Everything within the main loop will keep running indefinitely until you exit the program by closing the window. OpenGL's GL clear color function is used to set the values for red, green, blue, and alpha, which is the transparency value, all of which are clamped to the range 0 to 1. Therefore, within the main loop, we have some simple code that continuously bounces each of those three color values between 0 and 1. We then output the three color values to the console window, which we can observe while the program is running. We then change the color of our display window to the combined color of our red, green, and blue values by calling GL clear and passing in GL color buffer bit. Next, we have GLFW swap buffers. Quote from GLFW's window guide page under buffer swapping. GLFW windows are by default double buffered. That means you have two rendering buffers, a front buffer and a back buffer. The front buffer is the one being displayed and the back buffer is the one that you render to. When the entire frame has been rendered, it's time to swap the back buffer with the front buffer in order to display what has been rendered and begin rendering a new frame. This is done with GLFW swap buffers. The final function call within the main loop is GLFW poll events. Quote from GLFW's input guide page under event processing. GLFW needs to poll the Windows system for events, both to provide input to the application and to prove to the Windows system that the application hasn't locked up. Event processing is normally done each frame after buffer swapping. Even when you have no windows, event polling still needs to be done in order to receive monitor and joystick connection events. End of quote. After the main loop exits, we then call GLFW terminate, quote from GLFW's Introduction to the API page under Initialization and Termination. This function destroys all remaining windows and cursors, restores any modified gamma ramps and frees any other allocated resources. End of quote. The very last line in our program is exit, which is a C++ function call that performs various cleaning up processes. The next thing is to build the solution. You can see that the x64 folder which contains our executable is created automatically as part of the build process. Notice the compiler message after building is complete, which states previous IPDB not found, fallback to full compilation. If we now try to clean and rebuild the solution to eliminate the compiler message, it simply doesn't work. Now, although it's not critical, we can still adjust the project settings to stop this happening. So now if we go into the project settings, then select linker and then optimization, we can see an option for link timecode generation, for which we need to change its setting to use link timecode generation. Once we've done that, if we then build the solution again, we can see that the compiler message no longer appears. If we now look at the console window, we can see the changing colour values listed as control within the main loop. The program temporarily stops running after having clicked into the console window, but then resumes running after we press enter. We can also maximise the GLFW window to fill the screen, just like for any other window.